Hi everyone. I wanted to welcome you to the next class in data science. What I was going to do today is pick up where we left off last day. So we got to, after our discussion of supervised and unsupervised learning, particularly focusing on unsupervised learning, we got to just the beginning of discussing k-means. So this is an important algorithm in the sense that it's very widely used. It's an old algorithm, so it's worth explaining and getting to know the intuition behind how it actually works. And you'll find that k-means is implemented in pretty much all stats packages, and certainly the ones that we're using in class. So, for example, R. So, all right, so what k-means does is, as you can imagine, you're going to be calculating some kind of average, and the k refers to the number of groups. So this is something that gets applied in an unsupervised setting. So you need to imagine yourself having found some data, or perhaps generated some data, and you don't know exactly how the data should be partitioned. You suspect there are clusters in there. So for example, you may have many variables in your data, and what you'd like to do is see if you can find clusters, say, of patients. For example, if you think of the family data set we started the course with, if you were able to find clusters among those people in the data set, you could perhaps get to know something about them based on those particular clusters. So if you imagine, such as, for example, in the family data set, there were all sorts of measurements and details on the people in the data set based on there was a lot around weight, and there was a lot around, age and so on. That if you had a few more variables, for example, things like their activity levels, history of heart attack in the family, and other variables related to health, for example, you might be able to do something like clustering people for different health risks for different diseases. I mean, these types of things come out of the richness of the data set that you happen to have, but they also can come organically from data sets when they're unsupervised. So that's where different algorithms can help you solve those problems and look for those underlying clusters if you think that they are in the data set. And so we'll go ahead and do k-means and just see what we can come up with and see if we can actually find k underlying clusters. Okay, so what k-means wants to do is, what it's going to do is partition your data set. So every point, let's carry on with the example that I started with. Let's say you have patients in your data set with a lot of measurements on the patients. Every patient in your data set, or every point in the data set, will appear in only one cluster. So what you want to do is actually partition that space and have disjoint groups of patients that you believe are somehow related, and how they're related will be through the variables. And each will have some measure representing each cluster. So in this case, this gets called the centroid. The reason it's not called the center or the average, and it gets called centroid, is because there are different ways of constructing and calculating the center of any particular group of points or any particular cluster. And this is something I went over last day in class as well, that you can have many different ways of calculating what it means to what point should represent that particular cluster, for example. So we had some examples in class last day. So on the slides, on the third slide, the third point, each cluster is represented by its centroid, defined as the center of points in the cluster, which is not really much of a definition because we didn't define what center means, but we're going to define it somehow. So somehow this will get calculated. And what k-means will do is it will then assign patients to the cluster to which they are closest. And so what you want to do is minimize the variance between the different clusters. So for example, distances between data and the corresponding cluster centroid will be minimized. In a sense, they're getting assigned to their closest cluster, where closest is defined by how close it is to the centroid, how close each point is to the centroid. Okay, a couple of things you're probably already noticing. You might be thinking, well, what's k? It's a good question. So for k-means, you pick k in advance, and that's fine if you have some reasonable sense for what K should be. Like, for example, if I wanted to find risk of heart attack, or who patients I think are likely to get a heart attack versus ones who aren't, right away in my question, I'm kind of building in two clusters, right? So I may or may not actually find a good separation between these clusters in the data, but I kind of know that I want two, right? I want people I'm considering to have high heart attack risk and those who do not. So I may want to sort of focus on the people who have a high risk of heart attack, for example. Okay, so let's continue with the algorithm. A few other things are also dangling out there, how we define centroid, and then how we actually step through the algorithm. Okay, so here's the way the k-means algorithm actually works. So we have our unsupervised data. So these I'm calling here on this slide input points. So this would be, say, all the measurements of the people whom you're trying to group by their characteristics into clusters. So we start with an initial partition. So we've chosen K, and then what we'll do is just randomly assign people to different clusters. So we know we want K clusters, and so we just go and we kind of put people in different clusters randomly. So we have some initial starting point. And then from that assignment, so everybody is now in a cluster, and from that assignment, what we'll do is we'll calculate how far each point is from the neighboring centroids, and we'll just reassign that person, in this case person, but reassign the point to the closest centroid. Okay, and every time you do that, every time you change the composition of the cluster, you change the value of the centroid. So if you think of the centroid just as an average, if we have, I say 5 points, and I calculate a mean, and I put the 6 point in, unless that 6 point equals the mean, or happens to somehow exactly balance the data, we're going to end up changing the mean value if we recalculate it with the new point. So that's what happens in k-means. So you end up with different centroids. And so then you just start going back and forth. So now we can recalculate the distances from the points to the centroids, reassign the points to the centroid that's closest in some sense. We have to also pick our distance metric, something we talked about last day as well. But reassign and recompute centroids and so on. And so we just keep kind of going back and forth between those two steps, assigning points to their closest centroid, recalculating the centroid, assigning points, or like reassigning points to the closest centroid, recalculating the centroid, and so on for all k, and we just keep going through there until no points are changing between the centroids. In some sense, we've got stabilization in the outcome. You can get things like 1 point kind of flipping back and forth between two centroids and so on, but the idea is that you converge on assignment of all your points to those k the sort of k clusters that you have. Okay, so there's an example on the bottom of this slide that's a simple example, but it shows how the algorithm works. So what's going on in the very left panel of this set of 4 here is we've got some points. They've sort of got this U shape here. And then for some reason, we believe that there are 3 clusters underlying these points. So what I'm going to do is I'm going to pick a random partition of the points and calculate those centroids for the initial starting point for k-means. So we know we've set k equals to 3. We've got some way of calculating a centroid. Maybe it's an average in this case, so we just look for a spatial average here on the left. And then we're going to have some way of calculating distance between a point and a centroid. So in this case here, we could just use Euclidean distance, for example. So that's one of the distance metrics we talked about at the end of last class. Okay, so on the left, what's happened is there's points have been randomized into 3 partitions here, and then what we'll do is we'll calculate the 3 centroids. So the centroids have been marked with color. So you've got red, green, blue here. And then we'll go ahead and reassign points to closest. So you can see that they, in the next step, the points get associated with their nearest cluster here. Let's assume Euclidean distance to do that distance calculation. And so you end up with this partition over the space. Now what we'll do is move those points to their centroids, and then like if they're closer, for example, to a new centroid, when you do that reassignment, then they get assigned to that new cluster, and then you recalculate the centroids and continue to iterate. So maybe I need a couple more panels here where I would recalculate centroids and continue to iterate, because we don't have, these centroids don't actually move here. So really this is sort of the first step of assignment of points, really what's going on in the 4 panels here. Okay, so as I said, k-means is widely used, partially because it's simple, right? You can see this idea of having an initial random partition over the space. Those points create the first k clusters, computing the centroids, and starting to reassign points to the centroid that they end up closest to, and recalculating the centroids and so on. This is not. This is something that, if you know the number of clusters and you're confident in using whatever method you're using for calculating centroids and whatever distance metric, then you can generate those k clusters this way. And it converges, right? So you don't end up sort of going back and forth or whatnot. Okay, so like I said, it's simple. It's also pretty fast, so this is something that can be executed on a computer quickly. One thing that you might be thinking is that I did something random at the beginning with k-means. So I said I wanted 3 clusters in the case on the previous slide, and then what I did is I assigned all my points to those 3 clusters randomly, just as a starting point. And it turns out when you do that, how those points actually get assigned randomly can influence your result. So if you have a certain assignment of these points in your initial clusters, and then you start to calculate the centroids, reassign the points, calculate the centroids, and so on, reassign the points, you can end up with a different set of clusters depending on your random initial assignment. And so this is somehow very unsatisfying. Right? I mean, we're trying to do something where we believe we're uncovering real underlying structure in the data. So we think, for example, in heart attacks, that there's a high-risk heart attack group and a low or no-risk heart attack group, and we can really partition the space that way. And so we'd like to see that these clusters emerge from the data in a consistent way. And so running k-means several times and ending up with several different clusters or different people in the different clusters is somehow very unsatisfying. Okay, so that comes from the randomness in the initial assignment of the clusters. The other issue, as I mentioned, is you have to choose k up front. So if you're in a situation where you don't actually have a compelling reason to believe that there are a certain number of clusters in your data, or you don't know that number, then you have to take extra steps to justify k in this case. And there's been some work done on k-means where people have created simulated data sets where there is underlying cluster structure in there, and then looked at how good k-means is at pulling out or finding that real underlying structure. I mean, we know it's there if you're in a simulated data set and you create a data set that has those underlying clusters and then add noise, for example, and then test out whether k-means can uncover those clusters or do the clusters that k-means finds actually match those underlying clusters. And a lot of the times it doesn't. So it won't necessarily find that optimal configuration. Sometimes it does, but it's not guaranteed to find it. And so that's a worry, right? Again, if you believe that there is real underlying structure, you would really like to be able to rely on your algorithm when it finds some underlying structure that matches the real underlying structure. So k-means it's not the most reliable algorithm in that sense. Okay, so some people have done some work to sort of shoehorn k-means around this problem. So placing so if you choose your first centroid on a data point, and then you find another data point that's as far away as possible from that initial data point, and put your second centroid there, and so on until you get up to k centroids. They seem to putting that type of sort of broad range of centroids, if they cover your data well, that will help it find the true underlying structure in the cluster. Most of the time when k-means is implemented, though, it doesn't implement that first step. It does the randomization, the random partitioning that I mentioned for the first step. Okay, so you might find some things where people have done some modifications of k-means or updated the algorithm, for example, and it's to get around some of these problems. But really, in terms of things like simplicity, it's really hard to beat k-means. I mean, that's a pretty simple algorithm. Okay. All right, so finding k. In some applications, you might be really lucky, and you might just know what you expect k to be and have good theoretical reasons why you would expect that, and you can just blaze on if you're really confident in what k is. Many people will do things like try to learn from the data what they expect k to be. So let's say if there are two variables, what you want to do, well, if there are two factors to balance, so you want there to be you want the number of clusters k to somehow have low average variance of the clusters themselves. So in that case, what you would do is you want to lower this average variance of the clusters as much as possible. And what you'd like to do is have the smallest number of clusters that do that. So if you imagine reducing k and reducing k and reducing k, having smaller and smaller clusters, you maybe can find the sweet spot where you haven't increased the variance too much by lowering k, and you have a relatively small variance on each of the clusters. So you can imagine so for example, what variance means in this case, if you imagine k equals n, so you have as many clusters as you have observations in your data set, then each cluster is 1 point, and so you don't have variability, right? So you've increased k basically as big as you can, and you've really reduced the variance of the clusters. Okay, so that's great in the sense that your clusters are very, very low variance, but it's not great in the sense that k is very high. And in fact, of course, you haven't actually contributed any information by running that version of k-means on your data, because it'll just return the data set to you. So it's sort of a degenerate case. But if you start thinking about how increasing k can reduce the variance on the clusters, then it can help you see how that might be a criteria to think about when you're trying to find the optimal k for your data set. So you want that average variance low, so the cluster is kind of tight around the centroid. Okay. There are other criteria, too, that you would apply to the clusters. Bayesian information criteria, Ikake information criteria, Davis-Boulden index, confusion matrix, and so on. So like I was trying to introduce last day, there are, in many of these algorithms, lots of decisions that you're going to make when you actually implement them. This is yet another one. So what criteria do you use for finding k? And that's on top of the other things that we've had to decide in advance that are decisions up to the researcher, like your centroid calculation, for example. So are you using a mean, for example, or geometric mean, arithmetic mean? Like, well, how are you actually calculating that centroid? And then how do you measure distance? Right, so how do you measure the distance from a point to a centroid? And like I said, last day we went through some of those norms. It's only a few slides earlier in this slide deck, so you can always refresh your memory. Okay. All right, so that finishes up the introduction to k-means. I wanted to continue this discussion with some examples of classification and decision trees. They are closely related, and again, you're going to be using these classification methods on data. So I wanted to just push on our knowledge a little bit and try to think through some other ways that people have solved this problem. Okay. All right, so in classification, what we'd like to do is take our data, so in this example I'm calling our data x, and we can have continuous or discrete variables. So for example, with the heart attack data on the patients, you could have weight measurements, say, for each patient, and so those might be continuous, and you could have age measurements, and those might be discrete. They might be only integer valued, for example. And in this case, so for classification in this example, we're going to do supervised learning. So we have a set of labels here, script L from 1 equals up to K. So in the example with the heart attack, here we might have the data that are labeled with script K equals 1, 2, or 0, 1, for example, because maybe people had a heart attack or they didn't. And so if you think about when we went through the K-means example a few minutes ago, we did not have supervised data, and so we were hoping these clusters would emerge from the data by using the algorithm to allow us to group people into, you know, what in the example that I was using, into high risk for heart attack or low or no risk for heart attack. So you can see how if we're trying to do that with a supervised case, and we actually have our data labeled so we know who got the heart attack and who didn't, then that can help us, we can use that information to find rules in order to build those clusters. So for example, I could, if I wasn't in the original study that built those rules, for example, I could take all the same measurements of myself, like weight, age, whatever it is, all the variables that the rules were built on, and then just run it into the model that's already built, that was built on the supervised data, and see if I fall into a high risk or low risk categorization, for example. So I'm not labeled because, well, I mean, I guess I haven't had a heart attack at this point, but I don't know that I'm not going to have one. And so because we don't know the future. So really, the model's out in the wild, and new input data is being fed in. Okay, so our goal to find a classifier that allows us to predict the label of a new observation given a new set of features. So the new set of features would be measurements I had made on myself, go into the model, and then we would say, oh, she's high risk for heart attack, or she's not. You put me in one of the groups. So you're essentially assigning a label to me. Okay, so that's a supervised problem, as I said. And so one of the things that we talked about last day in class was different ways to ensure, or I guess you can't ensure, but different ways to feel more confident that you've actually got a good model or a correct model. And the primary way that people do this, as we were discussing, is they split their data set into a training side and a test side. And in class, I sort of gave some examples and said, sometimes people split it 50-50, 80-20 is the most common one I've seen. Some people do 90-10 and so on. So you might train on a larger proportion of your data than you test on, for example, or you could just split it in two. And you want to be careful when you're creating those, partitioning your data in that way, that you don't do it in some way that is related to the structure in your data. So you have to do it in a completely random way. So for example, if your data are sorted by age and you happen to have a lot of children and middle-aged people and old people in your data set, for example, and your data is sorted by age and you just slice it in the middle, you'll train your data set on young people and test it on old people. It won't look very good. So even if it's actually pretty good. So the idea is you want to have a representation for the different aspects of your data sets. So I would want to have a nice representation of young people, middle people, old people in the training data set. So you can do this by random selection, but you want to make sure that that's in there. And then when you test it, you also want to test it on the types of data you think you might see, for example, from all sorts of ages. So you want to make sure that those are represented in the test set as well. Okay. So we usually use a subset of the data, the training set, to learn or estimate the classifier. So F hat is going to be the label that we assign. So for example, F hat, when I put my measurement data into the model and I got some assessment, you're high risk for a heart attack or you're not, that's the F hat. Right? So what label did I get? And it's an estimate because we don't know the truth. I mean, if I had lived out my whole life and died, then we could look back and we would know whether or not I had a heart attack. But right now, we don't know. And then if we knew, we could see if the estimator was right, among other things. If I was dead, we'd probably be doing more than just that. Okay. so the so coming up with that label, F hat, what we'll do is we'll actually hide all those labels in the test set, use the model that we've created from our training set to go and create a new label for all the data, and then one of the things we could do is just count up how many we got right. So that's what's going on here. So we could, if we had labeled data where people were labeled as having a heart attack or not having a heart attack, or being high risk or not high risk, we'll erase all those labels on the test set, go ahead and reassign those people using our classifier, and then see if the labels match the underlying reality. So did the model come up with stuff that's right? And so what this equation says here is that we're just going to calculate some measure of, so yj here would be the labels, and f hat is our estimated labels of how close f hat was for each point, so each j, to the actual label for that jth observation. And then if, so for example, if they're right, we could say, give them a 0, so if we just looked at the difference, for example. And if they're wrong, then maybe it's a 1. And so what we do is we just do this over all observations in the test set, and if we do it, if we assign 0s and 1s like that, and we just sum it up, then we'll just sum up the number of errors that we made. Okay, hopefully it's really small. Model's doing a good job. And so one of the things to think about is you can see using a test set is going to be more instructive than if we use the training set. So if I trained this model on a particular subset of my data, and then I did the same thing here, but on the training set for both, I wiped off all the labels, fed the training data that the model had been built on, fed the training data in to the model. It makes some assignment of labels, high risk for heart attack, not high risk for heart attack. And then we can do the same thing. We can test whether or not that is correct. And they're certainly not always going to be correct, right? Or usually, I guess you could have a model that assigns everything correct, but it can come out all sorts of different ways. Like if you have a really terrible model, for example, you might not get very much right even on the training set, for example. But the problem with that is what you can do is, if that's your benchmark, what you'll do is you'll say, okay, I ran this model, tested it. Say if you're testing it on your training data, you'll say, oh, well, I didn't get everything right. I would like to get more correct, like more labels correct. And then you continue to work and you continue to tune the model until you can get to the point with just about any classifier where you will classify everything correctly on your training set. You just keep tuning and keep working until you actually get this. And so what you've done is you've confounded the validation of the model itself, so the classification model, with the training data that the model is actually built from. So you're not actually doing a real test of the performance of that classifier. What you're doing is sort of allowing the classifier to cheat in a way, because you're sort of showing it the data you're going to test it on later. So you've all been in classes where the instructor teaches you some material and it's sort of going through in a sort of really pedantic way, like one of these sort of, they've gotten some book from the publisher and they just go through the sort of the slides or whatever from the publisher. And then the test questions are really predictable, right? Like basically lifted sentences out of those slides and you just have to fill in the blank. You probably saw stuff like this when you were in elementary school. I certainly saw something like this. Hopefully you haven't seen it at college level. And you almost feel kind of like it's easier than if you actually had to really think about answers, but it's almost like you've been fed the answers in advance and then you have to spill them out. So that's kind of what it's like when you test your model on the training data set, or the same data that was used for coming up with the model. Really what you'd want to do, if I or your instructor wanted to know that you've understood things well, so you that's the equivalent of having built a good model, I would test you on independent problems, right? So I would come up with new problems and ask you how those, all the work that you've been doing previously might apply in this new case. And so that's when we start to get a sense of whether or not you've really understood the material, for example. So it's kind of a similar-ish idea with classification. So you don't want to kind of ask the model to work on things it's already seen. What you want to do is feed it new stuff and then see if it comes out with something reasonable. That's kind of what you want to do. And so, yeah, I guess that's not a bad analogy to think of it sort of like a mental model, except that's in the machine. All right. Okay, so here's the schema. So here's how our we're going to think about these algorithms. So if you look at this, this is the data set here, training set. Underneath it, I've got something called test set. So in this case, we've got 15 observations. So it's not a very big data set, but it at least allows me to write it on the slides. And then we've got an ID variable here, 1 through 10 in the training set, and then 11 through 15 in the test set. So what I've done is I've taken 2/3 of my data in the training set and 1/3 in the test set, so that's fine. And you can see it's labeled. This is supervised learning, what's happening here. I've got attribute 1, attribute 2, attribute 3, these are the variables that we're going to use to do the classification. And then we've got some class here. So these first 4 came up as no, and the 5th was yes, and no, da, da, da. Okay, so we've got these labels. And so what we're going to try and do is figure out, is there a relationship to the pattern of these data here, the way that they're a linked along individual, and the actual labeled outcome here. On the test set, we actually know in reality what this class is. We just split it off our overall data, but we hide that knowledge, right? So we're just going to put these reserved observations, their attributes, into the model, and then see what we get. So here's how the model works. So what we do is we've got some kind of, so we take the data, and that's going to allow us to build some kind of model. And we've usually got a learning algorithm that we implement. So in the case of k-means, we were learning where to actually create those k clusters. And as we shuffled points and recomputed centroids, that was our learning algorithm to try and converge on the k clusters that we wanted to partition the data into. So this learning algorithm continues, and we learn a particular model. Now, after the model converges, in the case of k-means, we stop changing the centroid, the clusters. Then we actually have our model. So this could be considered inductive reasoning because we're building this model from our limited set of data, limited in the sense that it doesn't measure the whole population. We've created the model, and we go get a coffee or something. No, we don't do that. But essentially, you do stop there and you take a break. And then what you want to do before you start telling the world about this awesome model you just created from the data that can do all sorts of prediction and come up with clusters and classify and so on, what you want to do is make sure that there wasn't just some weird quirk in your data, and this model is actually reliable. It's going to do a good job performing on new data. So you feed the new data in, and that's your reserved test set. Feed it into the model. Now this is deductive reasoning because we're not actually learning anything new here. What we're doing is we're just chunking through the actual specifics of the model. So feed in the attributes, and then you get in, it just goes chunk, 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 and then gets you the answer, whether it's clusters or whatever it is. In this case, we're going to classify into yes or no. And so it'll give you these estimates of these labels, yes, no, da, 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 whatever it is. And then we just compare how well the model actually did. And obviously a well-performing model is going to get a lot of those labels right. And we don't care so much whether or not the model gets test data set labels right, because it's going to do that because those are the data that the model were built from. Okay, so here are some examples. We already used the example of having patients with all sorts of measurements associated with them, like in my example, they were things like weight and age, and you could imagine a series of lab tests, blood measurements, and so on, all sorts of things that we could measure about people that might be related to their risk of having a heart attack. Another one, predicting whether a tumor is benign or malignant based on you can just kind of use your imagination on what you think would be related here. So I'm not biomedical expert, particularly what variables would be important to use in a tumor prediction model. However, you want to get the right ones that are actually informative and give you information about whether it's benign or malignant. Okay, so presumably you're building your model from good data. You have credit card transactions and you want to come up with an assessment of whether this is fraud or whether this is legitimate. Credit card companies are really interested in that. There's lots and lots of work they do on this. Phone companies do the same work. Any kind of anything where you're doing transactions, they want to know if they're real or not, particularly when there's money involved and people have an incentive to commit fraud, for example. Predicting the type of tumor among several types. So we could have a tumor benign or malignant, or we could be interested in, say, understanding what type of tumor it actually is. We're not restricted to yes-no classifications. However, I've been using them just because they're easier for me to teach when this is a new topic. I think it's easier to get your mind around. You can also imagine a classifier that had news items as input, so words, letters, and so on, going in to create the model. And then the clusters you're hoping to get would be labels on the type of news story. So can it pick the topic? Is a topic finance, weather, sports, etc., etc.? So you can imagine this might be done by certain keywords in there, but for unsupervised, you would want it to actually sort of find the clusters in the documents itself and not have those labels. We're in the supervised case here, so we would start with a series of stories that had that were classified like finance, weather, sports, and so on, and then we would test it on just some news stories and see how they came out, and then see if they got the labeling right. Okay, so classification is pretty general. So we've seen k-means. People have been very creative and imaginative in different ways to classify supervised data. For example, decision trees, rule-based methods. So under these circumstances, if this variable is less than that or more than this, then make this decision, and so on. So you sort of have different rules. Discriminant analysis, neural networks, naive Bayes, support vector machines. Lots of machine learning techniques have been developed around classification, more being developed. It's a very hot area of research. And we're going to look at a few examples. We won't touch on them all. We could probably do a full class on machine learning for classification. But what I want you to do is get a flavor for how these methods work, and especially what the underlying philosophy actually is. Okay, so let's take a look at the training data set from the previous slide. And instead of attribute 1, attribute 2, and so on, you can actually say what they are. So here's our ID. So we've got person 1, person 2, and so on in the data set. The question is, did they get a refund, a tax refund, in this particular tax year? And so if you had their tax return information, for example, you could just look at the amounts. And so person 1 got a tax refund, person 2 didn't, person 3 didn't, and so on. What's their marital status? Are they single, married, divorced? I think that's all we've got here, 3 options. And then we can look at also how much income did they make that was actually subject to tax. And so here you can see things like 125K, 100K, da 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 da. So the underlying question is, do you think there's relationships between whether or not they got a refund, their marital status, and the size of the taxable income that would allow us to guess accurately, up to some level of accuracy, whether or not they actually cheated on their taxes? And so in the training data, we have those labels. So we know that person 1 did not cheat, person 2 did not cheat, da da da. Person 5 cheated, person 8 cheated, and person 10 cheated in our training data set because these are labeled data. Okay, so what we could do, so this is a particular model, and I have not gone through how this model is constructed, but for example, here's one model for a decision tree. So we might look at the first variable. So did they get a refund? So it's only 2 possible things, right? They got a refund or they did not. So if they got a refund, according to our 10 observations here in our training data set, none of those people who got a refund actually cheated. So the ones who got a refund, number 1 did, number 4 did, number 7 did. These were all no. So with a very small amount of 10 observations, the model could just categorically say that if you got a refund, you did not cheat. So this also illustrates why building a model on 10 observations, even with as small as 3 variables, is just a really dicey proposition. But anyway, so let's just go with it for the purposes of the example, knowing that that's a little dicey. But that's why this stops right here with an outcome. So we look at refund and we're done if they got a refund. We just say they didn't cheat. So remember, the goal of the model is to come up with to fill in this red column here, whether or not they cheated, for data where we don't know the answer. So they got a refund, they did not cheat. So did they get a refund? No. Well, now it's not so clear because 2 did not get a refund, didn't cheat. 3 didn't get a refund, didn't cheat. 5 didn't get a refund, cheated. 8 didn't get a refund, cheated, and so on. And same with 9, 10. So it's not clear, right? So we need to put in some extra information. So we go to the next attribute, marital status. Well, so does this help us split our sample? So if they did not get a refund and they're married, then they're always classified as not cheating. So no, married, didn't cheat. No, married, didn't cheat. No, married, didn't cheat. So we can do the same thing we did in refund. Marital status, you're married. Nope, you did not cheat. We'll just, classify them and be done. Because there's no variability. Everybody who did not get a refund and was married did not cheat in our training data set. So okay, so that's a no. And then we've got something a little more complicated. So single and divorced, it's all mixed up. So we separate married from single and divorced. Single, divorced, we've got divorced, yes, they cheated. Single, no, they cheated. So maybe we can go ahead and use the income information to help partition the space as well. So it just happens to turn out, if you look at this, that people who are single or divorced, and then they filed with less than 80K of taxable income, those people just always ended up not cheating in our data set. And you can just take a look at that and verify that, like 60K, well, that's married, wait, single, single 70K didn't cheat. Okay, single 125K didn't cheat. Okay, so so we've got ones less than 80K didn't cheat, so we just go ahead and classify them as no. A greater than 80K we classify as yes. All right, so we've got some in here that they did not get a refund. I think we've got some that did not get a refund, single or divorced. Yeah, so here's one. So number 10, did not get a refund, so we split over to looking at married. Single, so we split over looking at taxes. Greater than 90K, that comes out on yes, so that matches our tree. Let's see what else. Single, 85, that also cheated, so that comes out on our tree. No, married, no, divorced. 95K, that also comes out as yes, so that also matches our tree. No, single, 70K didn't cheat. So we're going to isolate this one, this no, single, 70K, in no, didn't cheat. And then the other one's greater than 80K. Yes, they did cheat. Okay, so we built the tree, basically. I explained the tree. But you can imagine we built the tree, even though we haven't gone through methods yet of how we're going to actually build that tree. Okay, so that's the inductive reasoning component. And so now what we want to do is we want to test that this tree on new data. You can see if we have this kind of too finely tuned to the training data, we'll end up making mistakes. Like maybe this 80K is kind of arbitrary and being driven by this one observation 3 here that's at 70K and everybody else is over. Okay, but we'll see. We don't know that yet. Okay, so we could build this model, and these attributes here, where we're making a decision based on them, those get called splitting attributes. And notice it didn't matter that much. So the categorical variables that we have here, yes, no, single, married, and so on, we were able to split into two categories on both. So refund, yes, no, because there are only two categories. Single, married, what we did is married was consistently always no, so that got isolated out. Single and divorced didn't show any particular pattern, so they got lumped together. And then tax income was used to separate those. Less than 80K, greater than 80K. Okay. All right, well, let's continue on. Okay, so what about this tree? For example, let's suppose instead of starting with refund, we start with marital status. Okay, so marital status, we could do the same thing. Split on married. Everybody who is married in our data sets, this is the same data set. Everybody who is married, of course, we know from the discussion on the last slide, did not cheat on their taxes in this particular data set. So they just all right away get classified as no, and then we're done. We just exit the algorithm. If you're single divorced, things get more complicated. So we could look at, say, refund. Single divorced and you had a refund, then you end up with a no. Let's see. Single with a refund, no. Divorced with a refund, no. All right, so that puts you in that category. Notice we're splitting our data a little differently. This isn't just a different, a tree that's kind of got the same information. We're actually bringing out different partitions in the data set. Okay, single, divorced, and no refund. It's not clear because we've got people who cheated and people who didn't cheat still floating around in the data. So we would like another place to split our data. Hopefully this variable will split it into cheaters and not cheaters like what we saw before. Okay, so if we look at size of taxable income, we can actually do that. We'll split less than 80K did not cheat, greater than 80K did cheat. Okay, so those two trees that we go through and we classify people on the data, they look pretty different. So you can see that there's the decision tree for doing this classification is not necessarily unique. So just because you come up with one that gives you a classification doesn't mean that it's either the best tree, doesn't mean it's necessarily the unique tree, for example. So we're going to do a little more thinking about how to actually choose what tree might work best for your data. Okay. So here, what we've done is the first step, learning the model. We haven't gone through actually how to build a decision tree. I just presented two of them as examples based on this training data set. So we've done the inductive reasoning of building the model. We had some algorithm that so far hasn't been explained to you that created those trees. And then we ended up with our model, or our decision tree. So now what we'd like to do is actually go through and apply that model to the test data and see how the model performs. Okay, so let's take our first tree, and what we'll do is we'll follow all the way through the tree, just as I was doing on the slide. And so if we take our first observation, let's see, that's our first observation test set. No, it's confusingly, it's our second observation, but that's okay. It doesn't matter what order you take them through, as long as you keep your rows intact. So here we've got for person 12, attribute 1, yes, we know that from the previous discussion, that's whether they got a tax refund, so they got a refund. Small, medium, large, well, in this case we had married, single, divorce, so just ignore the fact that I'm not writing married, single, divorced here. And attribute 3 was their taxable income. Okay, so here, married. Okay, so let's say we've got refund, no, marital status, married, taxable income, 80K. So this is observation 12. And what we want to do is come up with our guess, use our model to guess whether or not they cheated on taxes. So we can just go through and flow. This is totally simple. We'll see refund. They can't go down there, unfortunately. They had no refund. So we have to go down here to marital status. They're married, so let's jump down the married corridor here, and then we end up with no, and so that person gets a cheat, no. Okay, so do you guys remember what the right answer was in the training data set? Okay, at this point you would look at what the right answer is and see if you got it right or not. If this person did not cheat, then your model is doing a good job. It's based on that one test observation. Okay, So all that's happening here is we're going to just go through and look at refund. It's no, end up with marital status. That's married. End up going down the married corridor here and ending up with no. And then we assign cheat to no. We say they did not cheat. And so that's something where you would you would never do it manually like this. You would create the tree in R, and then you would use a tree to predict based on test data. Okay, so let's continue on. So another way, so do you remember how when we talked about XML, we said you could have a tree representation for XML? Remember we had the plant catalog data? Or you could have a representation that is written in XML with tags, for example. And one of the things I emphasized is that it was important to feel comfortable taking a tree and writing it in with the tag structure, or taking XML written with tags and extracting the information and putting it into a tree form. So there's something similar when we've got the tree-based decision rules, the two models we just saw, in that you can actually partition the space. So you might have sort of had that sense as we were talking our way through the tree, because you are partitioning the observations, in that case the people, based on their attributes or the values that they have for the actual attributes. So this is what that type of partition looks like. So you might have some information about whether or not they cheated, and then you might be able to actually see these partitions across your actual data. So there's ways to represent these as on a graph, for example. So you might have the red circles being that they cheated, and the blue triangles being that they didn't, and then X and Y might be two of your variables. Let's see, this might be income, for example, and in this case it's continuous, but you could do it by categorical variable, or just plot another one of your variables there. And the decision rule will actually partition the space along, like similarly to what you see here. And that's what you want. So if there was a blue triangle in here, it's not fitting the data that well, or if there were red triangles here, the idea is to get these partitions to actually separate your data according to the labels. If it's impossible to do this, which can certainly happen if your data are very mixed up, or sort of commingled among each other, then you're just going to have a hard time predicting. There's just not a lot of structure in the data that you can use to actually do that prediction, and sometimes that's just the way it is. Okay, so let's take the iris data. So we talked about that in class last day as well. So the iris data is, it always comes default in R, so you can actually just, I think you can even just start using it. If you have problems accessing the iris data, I've put it on my website. So I wanted to also just warn you, when you see the, when I put R code, whoa, sorry about that. When I put R code in the slides, it doesn't render especially well, so I would not actually try to cut and paste this code into your R window. This code is here for you to run. I hope you run it, but I think you should retype it. And you can even just see that things are weird here. Like, look at like this petal length, it's supposed to be in quotes, and these quotes are pointing the wrong way. It wasn't meant to trap you or whatnot. It's just the way that it happens when I put it on the slide, and it doesn't render particularly in a friendly way, and that will cause problems when you try and run it in R. Okay, but you can't, if you enter in this URL, again, I think you should do it by hand, because okay, look, I've got a link here. This is awesome. So you can actually just link out and then grab that URL. Don't try and cut and paste directly from my slide, because I had to fiddle with this tilde to get it to, display properly here, and it's just, R is probably going to have a heart attack on it. Okay, but you can go ahead and use this command, read.table, to enter it into your R session if you want, or you can use the iris data that this comes in R. It's exactly the same thing. I created names here, so names of iris, sepal.length, sepal.width, petal.length, petal.width, and remember there were 4 attributes to the 3 iris types that were located in the data, and we saw the pairs plot last day, just showing how the sepal characteristics and petal characteristics could actually distinguish the different iris types. So library tree, so that might work in your R session. You may have to actually go and get the tree package from CRAN. So in RStudio, if you look at the top, there's a drop-down sort of drop-down menu called Packages and Data, and it will give you an interactive. So you just want to go ahead and make sure you load the tree. Sometimes if you just type library tree like this, the way I have, if you haven't grabbed the package first, it'll go, I don't know what you're talking about, tree. There's no such package. So make sure you get your computer or get your R session to go to CRAN, which is a repository with all the packages in R. It'll grab tree. Just do a search for it from within R under the Packages and Data menu. You want to load new package, and then you want to make sure tree is actually loaded to library tree. So hopefully this is all old hat to you now. We've been working with R for a little bit, but if you're getting things like tree not found or something, you'll have to just go through and load the library through the interactive session. Okay, we can use the tree command. So we've got iris.type here, so this is our label, and we'll model it. So what this says is, let's predict iris.type modeled on, the dot means everything in R, and we'll just get iris.type from data equals iris. So it would be possible, instead of writing iris.type here, to write iris $ iris.type. May as well just say data equals iris and make things a little bit easier on the eyes, but both would work. And we can plot. We've got text to add text to the actual tree plot. Okay, so that's how the code would look. You could predict on fewer variables, for example. So this is actually exactly the same code. Yeah, so we've got the same hot link here. So I go through the same things, the library tree. But here, what I'm doing is saying, for the tree command, predict iris.type based on petal width and petal length. And actually, the tree command can use petal width and use petal length to actually build the tree. It's not going to use sepal width or sepal length. And again, data equals iris. And we can plot the tree, and we have text. So I should have, okay, let's see if I can bring up RStudio here, because I went ahead and ran this. Okay, hopefully this isn't too crazy. Okay. All right, so ignore that top part there. Okay, kind of probably want to ignore most of this. Okay, so I went ahead and ran this, and what happens is something like this is what you get. So you have the tree output, and it comes unlabeled when you first run the commands, and then when you use the text command, in the slide deck is called stree, text of your tree object, and then it adds petal.width less than 0.8, all your decisions here and how you're gonna end up classifying. Okay, so this looks a lot like what we did. So we just used the tree library in R to do it, and what it thought. So we're letting it use petal width and petal length here. So the first thing it chose is split on petal width. If petal width is less than 0.8, then we just call it iris. We call it setosa. We just classify it that way. And if you remember from the pairs plot that I showed in class last time, just a little earlier in last day's slide deck, setosa was usually a bundle out on its own. So it's not and it seemed to be smaller. Remember when we discussed pairs plot last day? Like shorter and thinner petals. And so that's not surprising that on one split like this, on petal width, it just isolates setosa. And notice setosa doesn't come up here at all. It's that's your unique identifier for setosa. Okay, if petal width is greater than 0.8, then we have to go down this arm. And then the next thing that we actually split on is petal width less than 1.75. So that's kind of interesting. Notice we don't have to split on a new variable, which all our examples up until now in this discussion, we're splitting on a new variable. But it can just split on another range of our continuous variable. So this splits at a higher point on petal width and says, okay, well, the really, really big, really wide petals, we're going to go down that branch and say something about petal length, and the smaller ones will say something about petal length on this branch. So petal length, it's identifying 4.95 as a dividing line. Remember, think about that plot where we were partitioning our data set. So this is our partition line, and it says if it's shorter than 4.95, then call it versicolor. If it's greater, call it virginica, and same thing here. If it's less than 0.95, call it virginica on both, sorry. So we just, no matter what, we call it virginica this side. Okay, so that's the tree that R came up with. I strongly suggest you go ahead and try to implement the code and see if you can get this same tree. Back to the slide, that's all it is this particular slide of code here. So plot S tree, text S tree, and then we saw it do that splitting. All right, so this is the same ideas we saw in the previous slide where we had the scatter plot of points with the red circles and the blue triangles. All I'm trying to say here is that this decision boundary, like whether you're going to go down left branch or right branch, for example, ideally it would actually split your data perfectly like this. But it is going to, as you read the test data set, it is going to call everything on one side, one type like red plus, and everything on the other side, blue circle or whatnot. We're using straight lines to partition here. So if you have a curve or something that isn't running parallel to an axis, then this is harder for this type of algorithm. It might not predict as well. Okay, so for trees, again, we'll use some method of creating the tree, like for example, the tree package from CRAN. We'll build a model and take time to learn the model, and then actually go ahead and decide on what the actual model is, what our decision tree is. Okay, so what are problems with that? So we went through some of the issues, for example, that dog k-means, and as you might guess, since you're making quite a few decisions in all of these algorithms that you need to defend, like for example, your distance metric and how you actually do the partitioning of the data sets, for example, there's pros and cons. So similarly, there's pros and cons for these decision rules too. So the first one is we're splitting our records based on some particular attribute. And as you saw when we did the small example with the two different trees with the cheaters on income tax, if you start with a particular attribute, you can end up with different outcomes because you're optimizing some criteria associated with that choice of attribute. So you just want to be sensitive to how the splitting can actually affect the actual outcome. It doesn't mean it's necessarily wrong, but you want to make sure that that's really what you want it to do. Criterion for finding the best split. So do you want to split on refund? Do you want to split on marital status? What actually, how do you actually assess that one is superior to the other? We saw a couple of things with the tax return information. We split married away from single and divorced. The reason for doing that was that married, there was one homogeneous outcome, single and divorced had different ones, but we could have split three ways. I could have split on single, I could have split on divorced, could have split on married, for example. So how do we make those decisions, like how to split one attribute off from the others, or do we group them, or what do we actually do? Another example here, income, 80K was chosen. You might have been wondering about that because I think it was 75K or 70K that was actually below 80. So why didn't we split it, say, 76 or something? Why did we split all the way at 80? I don't think we had anything between 76 and 80, so maybe it effectively doesn't make any difference. However, it could. You might not have such clean data, for example. So how is it choosing 80, for example, as the actual place to do that split? So in the income tax example with the two trees, we continued to build the tree across all the variables, and we ended up being able to classify all of our training data through that tree. should we actually build that tree all the way to completion? So that's a relatively simple data set with 10 points, but suppose you had millions of points. You're going to end up just grouping bunches of hopefully similar points together, like-minded points, and you'll have to make criteria on where you stop building the tree or where you sort of cut the tree, for example. And here, previous example, stopped with all nodes being completely homogeneous. So we ended up being able to classify, and at the end of the tree, what we in previous classes have been calling the leaf, at the end of the tree we ended up with points that had traversed the tree in a similar way, coming out with the same label. You might not always get that. Okay, so if you remember, we had an example data set earlier that one of the attributes was small, medium, large. If you do have something like 3 attributes in a categorical variable, in this case small, medium, large, you can see there's at least, I guess you could not split at all, but if you're going to split, you can split 4 different ways. So you can split, everybody goes on their own branch. Small goes this way, medium goes that way, large goes that way. You can split with medium and small together and leave large out on its own, hive off small, hive off medium in the same way. There's different ways you can actually do these splits. So you should be thinking about how useful it would be if there was a way to evaluate how good a split is for building a model or building a tree. And luckily there are such ways to do that type of evaluation. You might, for example, train different trees and then use your test data set to decide which one predicts best, for example. That's one we already know about. Different splits for continuous variables. So here, taxable income, we made one cut at 80K. That's the way we decided to do it in our example. And you said, okay, you're greater than 80K, you're less than 80K, and this is how you do it. So there's obviously, with continuous data, many more different places you could split. You could do different types of split. We saw with the iris data how the tree managed to split twice on continuous data for where different labels fell in different ranges on the continuous variable, so the tree was able to make use of that. Okay. So for example, you could split many different ways with a continuous variable, less than 10K, 10K to 25K, 25K to 50K, 50K to 80K, greater than 80K. So it's not clear a priori how you might actually want to do that splitting. So we could do this in different ways. Right now we have the tree package and the tree function that just went ahead and did this, but as we'll see coming up, there's different parameters you can set and different ways to tune the tree and different ways you can actually control some of the outcome of the tree algorithm. Okay, choosing the best split. As I hinted at, we could come up with criteria. So for example, some numerical criterion for choosing among the possible splits. You could sort of start to infer from when we were talking about the 2 example trees on the income tax data, what would be interesting or most useful in prediction were ones that pushed labels together that matched. And so what that means, criterion should favor homogeneous or pure nodes. So you get to the bottom of a decision tree, like say you do something like cheated on the tax return, weren't married, single divorced, and so on. When you get to the end, ideally you would see something like cheated, 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 like the labels would match. Or you do something like refund no. Everybody who did refund no, if you remember, did not cheat. Well, I just said because they're no. But everybody who didn't get a refund also didn't cheat. I think that's how it went. No, everybody who did not get a refund didn't cheat. Well, whatever it is. So the actual labeling of that, that the group that was created, when you go down those branches of the decision tree, the labels all are the same at the bottom. So those are homogeneous or pure nodes. Okay, there's different cost functions, Gini index, entropy, also called deviance or information criterion, and looking at misclassification error. So I think what I'll do is I'm going to stop recording here and then come back and look at these different criteria for choosing the best split.